So the reason that we are doing all this really low-level stuff is for you to understand how different things are being used to really execute your queries. And what we are going to do is I want to make sure that first I have enough time to talk about transactions, but when we are done with transactions, we are going to talk about, given all that we know, what are some good indices to create and how can I tune databases, and that will basically set the stage for your last homework. So, but before we go into that, there's a topic that generally gets rushed, but it's a very important topic. I want to spend some time on it today and then continue on next week. So that is on transaction management. So we are going to talk about two separate aspects of transaction management. And as I tried to tell you that, the reason you would use a database systems as opposed to your own program, there are two basic reasons. One is query optimization, because you can write many different queries, but they are executed in they're executed in a way that's much faster than you probably can do with your own programming. The second one is transaction management, the fact that you can write programs that change data and that the database will have some guarantees. So there are two things that we care about. One is that you have concurrency. So what that means is that as you are changing data, many other people may be changing data at the same time. So multiple programs may be trying to change the same exact data item. This could happen for many reasons. It could be that, in fact, a single piece of item is being needed by multiple people, or it could be that you are actually trying to do something to subvert the system by, opening two separate windows and trying to register for the class at the same time, and you hope to see that nothing bad will happen. So concurrency means that multiple transactions may be executing at the same time, but we don't want that to cause trouble, right? The second one has to do with unforeseen problems. Known knowns and unknown knowns, that kind of thing. Or sometimes I call that acts of God or acts of Microsoft. So, your program may crash, your system may crash, there may be a power outage or a power surge, or there may be many different reasons that you may actually lose state. Meaning that you lose information that was in memory but not written to disk. Okay? So what that means is that, remember that we read data from disk to memory, we change it in memory, but until I write it back to disk, it is not final. So if you read data from a disk, let's say you are withdrawing money. I read that I have $200. I decided to withdraw $100. Then I changed the 200 to 100. I gave you $100, and power goes off. Somehow you had nothing to do with it, and then power comes back. I've given you $100, but the disk still says you have $200, right? So this is a problem that is not a problem for you, but it's a problem for the bank. But you don't want any of these to cause trouble, right? So the transaction management is going to make sure that none of these have a problem. So basically, remember we talked about, I don't expect you to remember, but I will write it anyway, that the database will give you some guarantees, even though these two things are fact of life, that you will have concurrency and you will have potential problems. And there are some things you cannot recover from, like disk failure, unless you actually have redundancy in your disk. But for other things of loss of state, you can probably recover from it. So we talked about things like atomicity. So one guarantee your database gives you is that if you did not complete your transaction all the way, it will have no effect, right? So this we called all or nothing. We talked a lot about that when we were looking at, triggers and so on. And then you have consistency. I guess when Stacy Patterson was giving her distributed systems class, every single student in that class came to ask me what consistency was. And I don't have a good answer. That it's just basically assuming that you as a programmer have written correct code, so that if I execute your code as is, you are moving the database from a good state to another good state. It kind of works together with atomicity. So your programs are correct. I should execute them completely and without changing. So I'm not going to write more. But the more important one is, yes, I agree that consistency is an ill-defined concept. But it's important to talk about isolation. When you write your programs, you don't really foresee that if somebody else tries to write this, I should do something. You just don't, right? You just basically say, my transaction is that I will subtract 2 from here and add 2 there. So regardless of what other people are doing. So I write all my programs as if I was the only transaction executing at a time. So all transactions are written as if they are the only one executing any point in time. Now this is very important. I write my program as if it's isolated from everybody else. And in fact, if I execute one program at a time, one transaction at a time, the database should be in a good state because I assumed you wrote good programs. So as long as nobody messes up with my data, it should be fine. But of course, even though you wrote it that way, it may not execute that way. And that's the problem that we want to solve. And the last one, that's also a very important one, called durability. That means that if transaction succeeds, its effects are not lost. And its effects are not lost even in the case of unforeseen circumstances. Even if you lose state, you are not going to lose any data. So these are the 2 things that we want to talk about. What kinds of methods there are to make sure that you can support isolation and you can support durability. So these are the 2 topics we are going to talk about. We are going to talk about concurrency management. That allows for isolation. And then we are going to talk about things like logging and recovery to ensure that durability is actually possible. Okay? So I will start with the concurrency first, and then we are going to go and talk about this one. So isolation is actually simple concept, but we have to actually have some sort of an understanding of what is a good transaction system or not. So I'm going to basically abstract the transaction into basically a sequence of reads and writes. So instead of kind of thinking of a transaction as a complete, sequence of SQL statements and so on, all I care is that a transaction, let's call it T1, basically reads some data and writes some data. So let's say that it reads X, and it reads Y, then it writes X, and then commits. So if transaction 1 executed fully, this is what it's going to do. It's going to read X, read Y, and then write X. Okay? We don't care what X and Y are, but let's say that they are tuples or they are certain attributes. Ultimately, as long as X and Y means different things, then it doesn't matter what they are. So I can have another transaction. Let's say this one will actually read X and read Z, and it will write Z and commit. And transaction 3 could be something like read Y and write Y and commit. Okay? And there are no rules that says which ones are good, which ones are bad. So it's perfectly fine that, that there could be a transaction that just writes something without reading something. That could be a valid transaction. We don't care. We are not going to pass judgment. So this is what I'm going to view a transaction as. Okay? But of course, transactions, since there is concurrency, they are going to actually interleave their operations. So there will be some rules. We don't know what those rules are, but because of different rules or because of which one gets executed first, these operations may occur in different orders. So the order that they actually occur in, I'm going to call that a schedule. So the schedule is the actual sequence of operations that take place in the database management system, right? So this is the actual sequence of operations that took place in DBMS. Remember that it's possible some operation just starts because I clicked the button. So T2 comes actually first, even though I named it T2. And then as T2 was executing, it had some amount of CPU time, and then my operating system said, okay, you had enough time, gave some time to T3, so then T3 executed some, right? And there could be other reasons that I gave more time to T1 and it executed differently. So I got some sort of a schedule, which is basically a mix and match of this. Of course, the operations will execute in the same order, but it could very well be that I first read of X, then actually transaction 1 goes to sleep, then transaction 2 reads X and reads Z and writes Z, and at which point, before it actually commits, transaction 3 gets some time, R3 of Y, and this is the point I'm in my current schedule. So in the schedule, this is what happened, these operations. And did any of the transactions finish? No. You basically assume that it is not finished unless you see commit or abort here, right? Otherwise, I have not necessarily reached the last operation. So schedule is basically, action in progress. And generally, we care about the point where transactions have not yet completed. So the point is that, for a given set of transactions, there could be many schedules. Another schedule may have the same series of operations. So this is schedule 1. A schedule may be something like this. What? We have not yet passed any judgment. Let's say that this happened, okay? This is like forensics, it's like CSI database. So let's say this happened. What can we say? And I'm just basically using the same exact operations, okay? It's the same exact operations, right? In the same order for each transaction. It's just that, R1 here goes R1X, R1Y, and W1X, whereas here it goes R1X, all this stuff happens, and then you have R1 of Y and W1 of X. Okay? So ultimately, the thing that I care about is which schedule is good and which schedule is bad, right? So that's the whole point of concurrency. So we have to have a rule of what is a good schedule. So what is a good schedule? If you know this by instinctively, if you know this by instinct, can tell me. What is a good schedule? What makes a schedule a good schedule? Yes.
One where you're not trying to essentially read a variable and write a variable. When you read a variable, you get what you're expecting. When you write a variable, it doesn't also read somewhere else.
So, for example, what you're saying is that if I had something like R1 of x, W1 of x, and R2 of x, and R1 of x, and R2 of x, and W1 of x, there's something different about these two, because here, this value is reading the value that's written by this, whereas here, this is reading the value before it writes, right? So this is kind of the instinct that we want to develop. But before we do this, okay, I'm going to give a much simpler answer, and then we will talk about this. So a good schedule is basically a serial schedule. A serial schedule means that everything for one transaction executes first, then everything for the second transaction executes next, and so on and so forth. So basically the idea is that all actions of one transaction at a time. So, you do everything for T1, you everything for T2, then you everything for T3, or you do everything for T1, then for 3 and T2. And the ordering doesn't matter, as long as everything for one transaction before the other one. Any of these are good, because transactions, you write them as if they were the only one executing, and if there was only one executing, then any of these should be acceptable, right? So a serial schedule is acceptable, ordering is not important. Okay? So if I execute one transaction at a time, then this is acceptable to me, right? That was the whole rule of isolation. But of course, I don't want to execute one transaction at a time, but I want to execute a transaction in such a way that it is serializable. Basically, the idea is that a serializable schedule is a schedule that has the same result as a serial schedule. So this is my golden rule. As long as whatever schedule you give, if it's serializable, that means its effects is the same as some serial schedule, then that's a good schedule. Okay? So basically, this is a very simple result, but it's actually a very restrictive definition. So how can two schedules have the same results? So two schedules have the same results if they read the same values and write in the same order. Okay? So let me try to explain to you. So this is exactly what we were just doing in a second ago. So I have R1 of x, W1 of x, R2 of x, and W2 of x. Let's call this schedule 1. Then I have schedule 2 that has R1 of x, R2 of x, W1 of x, and W2 of x. And I have S3, R1 of x, R2 of x, W2 of x, and W1 of x. Okay? So these are 3 possible schedules of the same 4 operations. And this one happens to be a serial schedule, because everything for 1 comes before everything for 2. Both of these are mixed, right? So now the question is, are these two equal to the first one? I need to write one more. R1 of x, W1 of x. I guess I cannot find one that satisfies this. All right. I guess I cannot find one. Okay. So is S2 the same as S1? No, because this is reading a value before it writes, whereas here it's reading the value after it writes, right? Okay. Is this 2 the same? Well, it's the same problem here, plus the last value written here is the one for W1, whereas in the top one is W2, right? So neither S2 nor S3 is equal to S1. So can I find one that is serializable here? Not for these 4 operations, I think.
You could flip R1, W1,
Right, but that would be a different serial schedule, but that would not be equal to this one, right? So then you can have R2 of x, W2 of x, R1 of x, and W1 of x, right? So this is another serial schedule, but this one is not equal to this one because, again, the last value you write here is W1, whereas here's W2, so none of these are equal. I mean, so the point is that they may actually be equal in some cases, but they are not guaranteed to be the same value, right? So ultimately what we are looking for is, we are looking for conflicts. You're looking for conflicting operations that are done by transactions. So the idea is that if a transaction writes a value and another transaction reads that value, this is called a conflict. So this is a conflict as well as the reverse is a conflict. Now, the idea is that these are conflicting operations, that their ordering matters. Okay? Since their ordering matters, if the ordering is changed in schedules, then they are not guaranteed to have the same result. So there are two types of conflicts. One is that you have a read and a write on the same item but different transactions, or you can have write on the same item by 2 different transactions. So these are all called conflicts. Okay? So read and write of same item by different transactions. Or write of same item by 2 transactions. So I'm going to rewrite the same thing. I'm going to say that two schedules are conflict equivalent or equivalent. It's the same thing if all conflicting operations occur in the same order. Okay. So that's really what we were looking for just a second ago. So let's try to write another one. So let's say I have R1 of x, R2 of x, read 1 of y, write 1 of y, and write 2 of x. X, read 1 of y, read 2 of x, write 2 of x, and write 1 of y, and I have read 1 of x, read 1 of y, write 1 of y, read 2 of x, and write 2 of x. I'm doing every computation, but still have not succeeded. All right, I'm going to write one more. I am rusty. All right. Okay. So I'm trying to figure out if these are conflict equivalent, right? So in this case, for example, let's look at S1. In S1, the only real conflict is W2 of x and R1 of x. So two reads on the same thing is not a conflict. You can do them in any order. But the R1 of x in S1 comes before our W2 of x, right? So if you have a schedule that reverses this, then you are not guaranteed to get the same result. So for example, here, this is reversed. So S1 and S4 are not conflict equivalent. So S1 and S4 may produce different results, right? So S1 and S4 are not conflict equivalent. But S3 and S1 are, right? Because you have these two, they occur in the same order. So S1 and S3 are conflict equivalent. So S1 and S3 are guaranteed to provide the same results because the conflicting operations occur in the same order. And since S3 is actually a serial order, that S1 is actually serializable because its result is equal to a serial order. So S1 is serializable because its effects are equivalent to a serial schedule. How about S2? All right. I was randomly writing stuff. So S2 and S1 are the same, and S2 and S3 are the same. So S2 is also serializable. S2 and S3 are same, so S2 is also serializable. So this is the basic thing that we care about. We want to make sure that whatever rules that I have in my database will produce schedules that are serializable, even though they may interleave operations. And my golden rule is this conflict equivalence. In fact, you don't have to really find an equivalent schedule. You can have a very simple algorithm. It's kind of an insult to call it an algorithm, but I will call it anyway. So you can check if a schedule is serializable very simply. So to check if a schedule is serializable, I'm going to draw, basically, first I'm going to find all conflicts. So it's going to be something like operator I and operator J, right? That means that transaction I does something that conflicts with transaction J before, right? Then I'm going to basically create a graph where each node is a transaction. And for each conflict, there is an edge. So let me write a simple one here. So let's say I have R1 of x, R2 of y, R3 of z, W3 of x, W2 of y, W1 of z, something like this. So now I have 3 transactions, T1, T2, and T3. And now I'm going to find all conflicts here, right? So the best way to do that is to start for, let's say, R1 of x, and then see if there's anything that involves x afterwards. So R1 of x conflicts with W3 of x, right? So this is a conflict. So T1 does something that conflicts with T3. I'm going to draw an edge exactly like this, meaning that in any order that I find, transaction 1 must come before transaction 3, because if it did not, then this ordering will be switched. So I want to make sure that all conflicts are occurring in the same order. I'm going to look at, again, now I'm going to look at R2 of y. The only thing that involves that is W2 of y, which is not a conflict. Then I'm going to have R3 of z that actually conflicts with T1 of z. So now I found that, in fact, T3 must actually come before T1 because of this conflict. This conflict. Then I have W3 of x. I want to do something with T2 here. Let's do T2. T2 is kind of like not doing anything interesting. Let's see, T2 reads x. Okay. After this. So since T2 reads x after 3 writes, so that means 2 must come after 3. And this is all I have. So this is called the conflict graph. If I look at all the conflicts, and I want all the conflicts to occur this way, then I have this conflict that says 1 must come before 3, and the other one that says 3 must come before 1. And then I have another one that says 3 must come before 2, right? So any serial order I find, I want all these conflicts to occur in the same order as they are in the schedule. Is there a serial order where all of these conflicts occur in the same order? It cannot be, because this is a cycle, right? You cannot satisfy this at the same time. If 1 comes before 3, then 3 may not come before 1. So this is the general idea, that if this graph has no cycles, then the schedule is serializable. If there is a cycle, then it is not serializable. That means that there is no serial schedule that is guaranteed to give you the same results as this schedule. So going back to the one that we had before, let me write one more. So I had this one, R1 of x, R2 of x, R1 of y, W1 of y, and W2 of x. This was for sure serializable. And I look at all my conflicts. I have R1 of x comes before this one. So all this one says is that T1 must come before T2. And as it is not cycle, this is serializable. So an eco-serial order is T1, T2. However, let's write another one. So R1 of x, R2 of x, W1 of x, R3 of x, R3 of y, W3 of y, W R2 of y, and W2 of z. Okay. This one? I think it's right. I think I did not commit to it when I was writing it. All right, so do we want to I'm just gonna throw that in just to see what happens. All right, so now let's try to do the same thing. Okay, so R1 of x does not conflict with itself, does not conflict with another read, so there is no conflict for this one. R2 of x conflicts with this, right? So that means 2 must come before 1. And that is all I have. W1 of x conflicts with 3, so that means 1 must come before 3. Okay. We are done with the x. Now I have R3 of y does not conflict with any of these. This one has W3 of y conflicts with R2 of y, so that means 3 must come before true. I already had accomplished my goal. Okay, so it's already a cycle. And then I have 2 must come before 1, which is already here, right? So this does have a cycle, so that means it is not serializable. Okay, so not serializable. Because it does have a cycle. If it did not have a cycle, what you can do is you can actually, so let's say my conflict graph was this. Since now this does not have a cycle, I can actually find a serial order. Basically, nothing must come before T1, right? Because there is no incoming edges to T1. So that means T1 can be first. Once I have T1, if I remove it, then T2 must come before T3, and then you have the last one. So if you have no cycles, you can actually find the serial order by finding the node that has no incoming edges, take that one, remove it, find the next node that has no incoming edges, and then continue until there are no nodes left. If you have taken algorithms, what algorithm is that? It is called topological sorting, right? Which is sorting the graph. All right. So what we are going to do next time is basically figure out if this is what we want. We want a serializable schedule. Then what we are going to do is try to find ways to make sure that you actually do produce serializable schedules. Now, I'm going to stop right here, but